You can dip into his time, don't worry about it. So, you take your 1 hour as planned, and there's no issue, right? So we will continue, and yeah, if you want to give tea break in between, if you think it's a good time, then you do that, or because tea is there for 11:30, whatever. Yes, sir.
So, ma'am, you are supposed to enable me.
Oh, you're not yet. Oh, sorry. 1 minute. Okay, yeah. Yeah, your co-host. Yeah, but why is it not? Oh, sorry. This one is. Yeah, you need. Okay.
And
Take it.
okay, am I audible to everyone here? And what about the participants who are joining online? Am I audible to all of you as well? May you please confirm?
Speak.
Yeah, am I audible? Is it fine?
Yeah, you are.
Okay. So, hello everyone. So, first of all, before beginning, I want to thank Priya ma'am and Najam sir for inviting me to give this talk over here. Oh, voice is quite low. Just let me try one.
Voice. Take it from here. Your laptop has.
Yeah, I can use it.
These guys also can. Yeah, continue. Just. Take it closer to you, Akshay.
This one. Is it fine? Okay. Okay. So here, as my ma'am has pointed out, I'll be talking about the cosmology. I do work in the field of cosmology, but eventually, when we were planning about like how should we plan these lectures, I'll be having 3 lectures, one today and two I'm going to take tomorrow. So the plan was that because a lot of audience is going to be from astronomy, some of you must be working in the astrophysics, a group of you are working in the field of cosmology. So we realized that it should be a topic of common interest. Okay. So that's why instead of talking about, especially about the cosmology or a project or my work, I'll be talking about a binding factor in all 3 aspects, and in generally I'll talk about that whenever you do any sort of sciences right now, either do humanities, you go into finance, economics, you do sciences, this particular factor do come together. In all the broadly, if I talk about any sciences or any analysis that you generally do, okay, its voice is still very faint for you.
ये माइक इस्तेमाल करेंगे क्या? हाँ, तो अच्छा आप जोर से बात कर लो.
Fine. So anyway, myself is very loud. So whenever we start talking about any field of analysis, one binding factor is, in general, you do have certain theory which you are supposed to analyze, or you want to predict, or you have modeled. On the other hand, then you come across with certain observational data. In the field of astronomy or astrophysics or cosmology, that could be observational data. In general, if you are working in something like experimental physics or you are doing some survey, then you are having some experimental data. Okay, but when you have these experimental data and these observational theoretical models, then how can you say something about, how can you make any sense out of these two different features or two different aspects? So here comes the role of statistics. where this statistics play a role, binding role, where you are going to utilize the observations to predict something about the model that you want to work with. So I'm also going to talk about the same aspect. In general, statistics is a broad subject. You can learn it for the years, you can learn it for the semester. So it's a bit challenging for me to give you something fruitful within 3 hours. So the aim of this session would be that by the end of 3 lectures, you must be able to learn certain tools which you can utilize further in your respective field or respective problem. So we will try to focus on that particular aspect. Secondly, this is going to be a bit of hands-on kind of, all of you are not having the laptops right now, but I'll show you some particular course and certain way of doing the things. Later, I'll give you some problems as well, maybe over the night by tomorrow, in case you can go through those problems, try to give a hands-on on your own, and then we will have a discussion about that. Okay, I'll continue with tomorrow with that point. Okay. So now in general, if we start talking about the statistics, very broadly, in the sense you can divide it into 2 aspects. One is going to be descriptive statistics and the inferential statistics. When I do talk about descriptive statistics, then it focuses on the particular aspects of the data where you are not analyzing the data in the term of inference. You are not concluding something about the data. Instead, you are just putting certain description related to data, like you are finding out the mean, median, you are finding out the variance, skewness, kurtosis, all the different parameters, and you are just putting them in a way where one can easily interpret that particular data. So all these kind of statistics do come under the preview of something called descriptive analysis. But we are going to focus on the different aspects where we are going to talk about the inferential statistics, where the task like you having a model and you want to say something about the parameters related to that model. You have 2 models, you want to compare these models, which one is going to be better. You want to do some, you are having certain hypothesis, you want to test that particular hypothesis. In all these aspects, in these all kind of issues, you want to make some inference out of data. So that aspect is going to be inferential statistics. That's also going to be a broad topic. Even this particular topic, we are going to zoom further. We'll be talking about one thing very broadly and in detail. That's going to be the parameter estimation. Okay. So parameter estimation means you are having a theoretical model data, and now that model is going to have multiple of parameters. How to make certain sense out of it, how to get some inference out of that particular data and model. That's what we are going to focus. Okay. So broadly, that's how we are going to zoom in our topic. So all of from the very beginning, like from the BSc first year, like even if I'll not start with from the intermediate, from the very first, whenever you go to any experimental lab, you start collecting the data. And in our maybe 5-10 years back when I was, or 10 years back when I was doing my graduation, or 12 years back to be exact. So at that particular time, we used to plot it on the graph paper. Yeah, used to plot the data and used to fit it in line. Now most of the students start doing using the computers. At that time, you were not having all that freedom and access to learning of the computational languages. Now there are some 2 aspects we are going to talk about. Very basic data analysis, the kind of least square fitting chi-square analysis. I'll just very quickly go through that. I'll not spend a lot of time, but later we are going to switch to the parameter estimation, which is going to be very useful in the field of cosmology when you have multiple parameter space, how to deal with that kind of problem. Okay. So here in general, that this is the very standard problem. BSc first year student can even try to attempt it. You have some observation, you went to the lab, you collected certain data. This is a linear data that you are collecting. Then you are supposed to fit a model, and that's a very simple straight fit line. This you can easily fit by using the least square fitting method. The method is very simple. You define something called square residual error, which is defined, we generally define it as something called chi-square. I hope most of you must be familiar with this. Are we good? Anyone who is not familiar with the basic chi-square? Okay, I'm considering that you are familiar with. Yeah, okay, thank you so much. So basic chi-square you can define. So this is the observational data. If you go back, this is the observation you are having. This is the x parameter and this is the error in the y. This is the theoretical model that you are having. We defined this something called chi-square. The whole purpose is that we should fit a line in such a way that we should fit these parameter a and b in such a manner that this chi-square should be minimum. That's why one approach for in the case of least square fitting, you can minimize this chi-square with respect to a and b, that del chi-square by del a put it equal to 0. You will be getting two equations. Further solve it further, then you will be getting this formula for the a and b, and you can also find out the associated error sigma a and sigma b. So eventually what we are doing, we are trying to find out the value of these parameter a and b parameter in such a way that where the chi-square is going to be minimum. And these parameter a and b parameter, we call them the best fit parameters, best fit values corresponding to this data and this particular model. This is very simple. I'm going to provide the code for this. You can go through, you can write down your own code and you can play with it. Okay. So, but now the issue arises. So eventually the same thing, if you are having, so you are trying to figure out, so if you are going to choose a particular parameter, let's say a parameter, plot the chi-square with respect to it, you can easily figure out that corresponding to certain point where chi-square is going to be minimum, this particular value will be calling the best fit value. In one parameter model, it's very simple, but the moment, because let's say talk about this problem only, here you are not having only one parameter, you are having two parameters, a and b parameter. The moment you will go into two parameter space, then when you plot the when you are going to plot the chi-square, like sorry, am I repeating the same slide? Yeah. Okay, just focus on this one. If we are going into the two-dimensional space, then you will not be able to find out a single minimum. Instead, you are going to have, so this is an inverted plot. You can obviously, it's a 3D plot, you can invert it, but you can figure out on the x-axis here is a, on the y-axis you are going to have the, it's not working, I think. Battery is done.
Maybe charge.
So here you can see on the one axis, on the, if you'll just see the xy plane, one parameter is having a value, another parameter is having b value, and then you are having this chi-square inverted. So eventually the aim is in this particular space how to find out the minimum value corresponding to this. Okay. The moment you find out the minimum value, you can plot the so you can plot this one and you can take the you can project this whole curve on the xy plane. So whenever you might have seen gone through the different papers, you might have seen we do plot the data in xy plane in generally in the form of this contours. Okay, in the two-dimensional contours like this, in the xy like a and b plane, I can say for now. And here the point which is going to over here, you can see this point is over here, this you call the best fit point, and corresponding to that you plot these contours. These are 1 sigma, 2 sigma and 3 sigma contours. When we do talk about 1 sigma, 2 sigma, it means the 1 sigma error. In the generally when we do talk about the Gaussian distribution, 1 sigma error corresponds to 60% confidence level. 2 sigma error corresponds to 95% confidence level. Okay, I'll be talking about what do I mean by this confidence level, but in a while. Okay. Now, this kind of analysis is very simple when you are doing for the parameters like a and b, when the parameter a and b are linear. The moment you are going to have something which is not linear, let's say you are having, so when I'm talking about linear, in linear, let's say you are having a data which is exponential. Okay, so you want to fit the exponential data, you can always take the logarithm of the exponential data, you can always convert it into a log form. Similarly, if you are having a model which is power law kind of, again you can take the logarithmic of that, you can always convert it into a linear form. So if it is possible for you to convert your model into linear form, then the least square fitting will work for you. But the moment you are going to have this functional form where you have data but the functional form is not linear, it can be any non-linear complicated function depending on multiple parameters, then obviously this approach, this particular formulation that I have shown you, this particular formulation like A and B, you cannot explicitly define A and B in a functional form. Over here you can see, just do these summations and put the value, you can directly get the answer. In that case, it becomes a bit challenging how to analyze this chi-square. Okay, now y observation, you know, this is a non-linear function. Y theoretical, I am talking about having parameter A and B. Now there is a very traditional way of doing this. Okay, generally what you can do, because the ultimately aim is to find out the value of chi-square for which A and B, find out the value of A and B for which the chi-square is minimum. That's what we want to do. So one can do one thing, you run a for loop on A values in the program, run another for loop. So in a nested for loop, you can say one on A and another on B. Keep giving the value of A and B. Keep calculating the value of chi-square. You make a large collection of A values, B values, and corresponding chi-square values. You can write down a program. That's a simple function. You can define a function, find out the value on that particular parameter. Then you can write down a sorting program in such a way to figure out what value out of, let's say you calculated 1 million combination of A and B, figure out what is going to be the corresponding minimum chi-square. That chi-square, you can say this is minimum, and corresponding to it the value of A and B are going to be minimum. This is a traditional way one can do it. Similarly, one can plot the contours around it, find out the error. But this is not a very robust way. Okay, with two parameters, if you are working in the field of cosmology or anywhere, or any sort of statistics, if you are doing with two parameters, this approach can work. One thing you can easily see, if I go here, this particular curve I am plotting for 2D, where on x-axis you are having A, on the y-axis you are having B. But think about if I am having 4 parameters. Let's say you are having a theoretical model which is having 4 parameters A, B, C, and D. Then would it be possible for us to plot it in the 3D space? Then, because for that we will be needing a 4 parameters, one axis for this curve, we will be needing a 5D space. We cannot plot it. And obviously the behavior of parameters, this particular curve along the x-axis you will see, and behavior along the y-axis, that might be very complicated in higher dimensions. So it becomes very challenging for us to use the simple chi-square approach to find out the best fit values corresponding to this data. Okay, so eventually that's why we try to switch to some other alternative ways of looking into the data. Okay, so for chi-square, I just don't want to give the hands-on, because otherwise the whole session will go into that. I want to do something called Markov's and Monte Carlo methods. That's going to be more, I think, of more interest for everyone and going to be useful as well. Okay, so I'll provide you some programs related to it. You'll go through them. In case stuck somewhere, you can obviously come back to it. Now, this is the task eventually we want to kind of approach. So that's why what I'm saying, doing that particular analysis, if you run this particular contours, you can always find out the value of A and B by using chi-square. Fit the data, you can see these are the data points here. Let's say for some random data I'm talking about, you fit a straight line. These dark lines are 1 sigma and 2 sigma error bars. This kind of analysis you can easily do with the chi-square. But if you are moving ahead, you are going to a approach where the parameters are larger in very larger in number. Okay, then how to go ahead with this? Just to switch to that topic, I just want to ask you one thing. I think most of you might be familiar with the numerical analysis methods little bit. So you must have solved the different sort of integrations by using numerical methods. So for one-dimensional integration, finite integration, if you do, you learn about some methods called trapezoidal method, Simpson 1/3, Simpson 3/8, Gauss quadrature method. Have you gone through them or are familiar with these methods? Okay. So all these methods you can easily implement when you are working in 1D finite integration. Have you ever tried to solve the surface integral, volume integral, or higher dimensional integrals ever? Anyone knows any method which can be used to solve these kind of integrations? Surface integral, obviously analytically in our vector calculus we do solve all these things, but any numerical methods of doing the surface integral or volume integral? So if you realize we are facing the same issue, Even when you will be doing the integration, if you remember trapezoidal method, in the trapezoidal method you find out the area enclosed by a curve. That's what do we understand with the area in the 1D at least. So over there what you try to do, you plot the curve, you can divide the whole area into the small bins. If I'll just try to write down, let me see if I can write down. So what you try to do, okay. So if you are having a curve something like this, some fx function, then in the trapezoidal method or Simpson 1/3 method, in these methods you will divide this particular area into small bins and then use different mathematical approach depending on the method to find out the exact area enclosed by these particular small bins. Generally, in the trapezoidal method, we consider that this area, we choose this to be so small that it's a straight line. We consider it to be a trapezoid and find out the area of a trapezoid. Sum it over. That's how we do. But now try to think about if you are having a volume integral or a surface integral or higher. The people, students working in the field of high energy physics, you are supposed to sometimes integrate up to 5, 6 or 10 parameters. Okay. So then that's a higher dimensional space. Even these traditional numerical methods, when you will try to go into higher space, these methods will not work. Similarly, when you try to do the parameter estimation and you want to go into higher dimension, more than 2, 3 or 4 parameters, again these traditional methods will not work. Then we came back to some methods called Markov-Chain Monte Carlo method, or Markov-Chain per se. Monte Carlo we'll talk about later. Okay, so that's why even for doing surface integral, volume integral, we revert back, we came back and we use the Monte Carlo methods, Monte Carlo integration. Some of you must be familiar with Monte Carlo integration methods. Okay. Now, how to approach that? Before that, before jumping to the Markov chain, I just briefly want to talk about something called maximum likelihood. Okay, maximum likelihood approach or method of analyzing the data. So generally, if you'll see calculating the chi-square, in the chi-square comes, means when you do talk about statistics, you can do the statistics in, classify the statistics in different domains. So first classification I did inferential and descriptive. I further want to classify the statistic in two approaches. One is frequentist approach, another one is the Bayesian approach. This is the way we use the probability in the field of statistics. Based on that, we can classify the statistics in two domains. When we do talk about the frequentist approach, in the frequentist approach, we consider about probability to be an absolute experimental quantity. So let's try to understand it this way. If I am a frequentist person who believes in the frequentist statistics, and you give me a coin, okay, and you'll ask me, if I toss it, what is the probability of finding out the probability of getting head? So what I do, if I am a frequentist, I am going to toss it 1000 times. I'll calculate how the outcomes of head, outcome of the tail, and then correspondingly divide with the total outcome. So for me, the probability is going to be the possible outcomes divided by the total possible outcomes. That's how, as a frequentist, I define the probability. Obviously, if you are going to do this exercise 1000 times, even then probability of even then the chances that you will be getting probability to be 1/2 are going to be very negligible. You might get 0.49, 0.5 on something of that sort. If you'll repeat this exercise for millions times, then you might approach to exactly 1/2 or this approach. But if I am a Bayesian statistician, then what I'll do, I'll assume that my coin, I'll make an assumption, I'll make a prior assumption about the data, about the coin. I'll assume that my coin is unbiased. If my coin is unbiased, then the probability, then inherently I'll assume the probability of getting the head or getting the tail is going to be half. Okay. So if I'm a Bayesian statistician, then I'm going to use the probability for that purpose. Okay. So similarly, when we do the chi-square analysis, I'm not talking about any probability. That's why chi-square analysis can come into the preview of the frequentist approach. Now, if I, as a Bayesian analyst, if I want to work, then I have to, corresponding to every observation that we do take, I have to talk about the respective or associated probability with that observation. Okay. So now, I hope some of you must be remembering the data file that I have shown to you, all of you. So if you see, I am talking about the observational data. So observational data over here, assume that, okay, I'm missing that x right now. So there is a xi as well. Xi corresponding to xi.
Oh, sorry. It's okay.
Remove pen, you'll have to remove.
Remove.
This one.
Remove pen.
This.
It's okay.
Now give full view. Full view. 1 second. It's
From here you have to do.
from here, not here. No. View options. No, 1 minute. You have view options. What is this hide video panel?
Yeah.
You're back. My problem is my photograph is coming, but it's not coming on YouTube. So YouTube में I'm not there. इसमें आ रहा, YouTube पे नहीं है. ये इसमें है, देखो, इसमें है.
So now what we are trying to is it visible to everyone? Yeah. So now what we are trying to do right now, let's say we have some observational data, xi corresponding yi values and the associated error. And now let's say again as a I want to use the Bayesian approach for calculating this theoretical term where I am having theoretical model, again the linear a plus bx line. Now how I'm going to start this time what I'm assuming that corresponding to each error, so each parameter, let's say this data that I was having over here, let's say this is my first observation, I'm going to make some assumption about it. What assumption I'm making? I'm going to assume, and I'm assuming this when I'll be doing my analysis, that this particular single observation is coming from a probability distribution. Okay, so corresponding to first point there can be a probability called P1. Corresponding to second point that can be P2. Corresponding to third point that can be P3. Okay, this is first assumption I am making. Second assumption that I am making for my analysis, you can make or not depending on that analysis will change. I am considering them all these observations are independent to each other. So if all the observations, first one, second one, third one, all of these observations, they are having a probability distribution associated to themselves and all of these are independent, then what we can do, we can always define the probability corresponding to each point. Right now don't think about this is a Gaussian one, I'll talk about it, but consider it to be P1, P2 and P3. Let me write it here. So if you are having corresponding to first point, you are having P1, then P2 and P3, then you can always find out something called joint probability distribution function. Yes. So the total joint probability distribution function is going, and if these points are going to be independent to each other, then you can P2, P3 and like this. If you are having n data points, you will keep writing. Okay. So you will multiply all the probability distribution function. That's going to be our joint probability distribution function. Now, in the field of cosmology in general, you will see a trend, and even in multiple fields, I'll say for that purpose, we generally see this trend that we assume that these independent data points are coming from the Gaussian distribution. Okay, sometimes we might be knowing, if you are doing an experiment by hand in the lab, then you might be knowing, okay, if you can repeat it multiple times, you can plot the outcomes. In the first steps, you must be remembering when we try to calculate the value of G, gravitational constant. Yeah, sorry, small g, acceleration due to gravity. So we try to repeat our experiment 1000 times, then plot the histogram, and we realize that it's a Gaussian. Over there, you know that it's going to be a histogram and a plot which is Gaussian distribution. But what is happening in the case of astronomy, cosmology, and astrophysics? You are taking an observation of a supernova, let's say. Now that particular supernova event is taking place only for once. You cannot, that's not your lab. You cannot go in the kitchen and you can keep preparing the recipe again and again and you will keep testing different outcomes. That's not possible for you. So even then, it's very kind of in tradition that we assume that each and every point do come from the Gaussian distribution. So those of you who are working in the cosmology might have worked. Can you try to tell me what can be the justification behind it? We generally do this exercise. Anyone want to add on this? Have you heard about something called central limit theorem? Anyone who is familiar with central limit theorem? Okay, there is a term in the statistics. We'll talk about it. If I just want to get an idea, in case otherwise tomorrow's lecture I'll talk about it. In general, central limit theorem, the theorem states that whatsoever. So I just will focus on the central limit theorem tomorrow, but that particular theorem gives us a freedom to define these data points to be Gaussian. So Gaussian, that's why it's very much tradition. Why and how we'll do tomorrow. Okay, you can note it down. Maybe in the evening you can go through this particular thing, read up a little bit about it, and then when we will come tomorrow, we'll discuss about it. Okay. Right now I'm just giving you the name. So right now what I'm assuming over here, I'm assuming that each and every point is coming from a Gaussian distribution. So it's 1 by 2 pi sigma, the form Gaussian form you must be familiar with, corresponding to each point. So I can multiply all the P1, P2, P3. So this is going to be the product of all the probabilities. This joint probability distribution function, in this case, we generally define it by this parameter called L, and we call it something called likelihood. Okay. Now have a look on this particular likelihood, and next slide if I'll go. Yeah, this is the multiplication of all the likelihoods. I'll take the log of both the sides. The moment we are going to take the log, you will find out this parameter will get reduced to this form. So there will be some constants as well. I'm getting rid of them because when you are plotting it, a constant is just going to shift the scale. It's not going to change the maximum minimum. So can you see one thing? If I am considering it to be a Gaussian, given the condition, then considering them to be independent, and if I am defining my likelihood, you will find this form familiar. This is the form of chi-square that you have already defined earlier. Okay. What do we try to do? We try to find out chi-square to be minimum, but it's related to this likelihood with a minus sign. So we can focus on one approach. Either you write down a chi-square, find out the minimum value because that's the square reduced residual error that you want to calculate, or you define a likelihood and trying to find out the maximum. So eventually this method of finding out the maxima of a likelihood, we are going and further using it to find out the best fit parameter. We name it maximum likelihood method. Okay, I think nomenclature is clear. The main challenge is how to maximize something of this sort. Likelihood. So this is the likelihood you will see. This is a complicated function 1 to n. You will see parameters is still a and b, but that's going to be a complicated form. Now the task for us, we are supposed to find out the maxima corresponding to it. Now if it is a 1D, this is a function of a and b. You can plot it. You can visually, at least you can get some idea. Then you can zoom it further. You can even visually, by just using the plotting, you can find out the value of a if it is a single function in 1D. If it is 2D, even then it's possible for you to plot a three-dimensional plot. You can still see where the maxima is going to lie. But the moment I'll talk about 3D, 4D, 5D or higher order parameter estimation, it would not be possible for us. So then we have to look into some robust way of finding out the maxima corresponding to this one. So for finding out the maxima in this particular likelihood, there are multiple approaches. There are some optimization methods as well, but again we are not going to rely on them. The method of maximizing it we are going to focus is going to be Markov-Chain Monte Carlo. That's the problem. From here, this is the brief introduction about the problem. Here onward, I'll be talking about Markov-Chain and Monte Carlo method. Okay. Anyone having any question till now? Yes.
So we have considered the Gaussian thing.
Yes.
So if we don't do that,
Yeah.
the system will be more complicated.
Then system will be more complicated. Then you can always see corresponding to first one there is going to be P1, another to P2, then one is considering it to be coming from some Poisson distribution, some coming from beta distribution. You can always form a very complicated likelihood. Then again it will be very challenging. Yes, that's very much true. It need not to be Gaussian. We are choosing it to be Gaussian because we don't know what kind of distribution is kind of inherently lying over there. And if we don't know anything about the system, I'll prove it to you through the central limit theorem tomorrow that it's best to assume it to be Gaussian. We are safer to assume it to be Gaussian. Okay. So if you know, then you should use the exact real inherent form of distribution given distributed under the parameter. Okay. So if you have any question till now, then we can ask. Otherwise, we can take a break. Then we can. Yes, ma'am. In case, is it the time?
Yeah.
Yeah. So yes, please. Continue. We'll take the questions.
Just one question. Related to that, maximum, if it is not a Gaussian,
It's not a question.
then we can use maximum likelihood.
See again, maximum likelihood you can use anytime. So if you are what the likelihood, if you are multiplying the probabilities, that's going to give you a joint probability distribution function. Joint probability, that's it, going to be a distribution again. So you always, if even if it is Gaussian or not Gaussian, it's always going to have some maxima minima in the whole space. Then your aim is to pinpoint to that particular maxima. So next problem that I'm going to deal with, I'm going to talk about, I'll not take a Gaussian, I'll take something else, some random distribution, and then we try to figure out how can you approach that. I'll do it in 1D, 2D, and then we can further extend discussion up to higher dimensions. Yes, please.
So, if there is any increment in the dimensions, like you mentioned.
2 to 3, 4, yes.
Yes, sir. So, is it possible to use the method of gradient ascent?
Which one?
The
Gradient
Gradient, that one you can use, but then that will further come, because see, even in the gradient descent, the challenge would be, one of the thing, can I answer it in the second session? I'll answer this, I'll keep it in mind. Okay, I will show you something, then I'll answer it.
Yeah.
Yes.
Is it not required to first understand what is prior and then go to the likelihood?
So still I am not talking about Bayes-1. I haven't introduced Bayes-1 till now. I'm just talking about likelihood. The moment I talk about prior, if you have done, then I have to talk about posterior. So that's why I'm calling it the maximum likelihood, not maximum posterior method. Okay. So prior we will talk about it. So firstly, we'll just learn the algorithm, what is Markov chain and Monte Carlo. Then we'll talk about the basic related statistics. Yes.
इनका फोटो क्यों नहीं है?
वो
सबका है, वो सब
No, it's not.
उनका है।
It's not. It's very much possible that you are going to have a error matrix where you are going to have, you are familiar with the variance matrix or error matrix. So in the case of independent parameters, you are going to have all the diagonal terms, all the non-diagonal terms are going to be zero. But the moment you are going to have some correlation between the 2 points, and that should be there. See, eventually try to think about, you are doing an experiment, you are calculating the error. Obviously, if you are using the same instrument, there are going to be systematic errors plus the random errors. If you are using the same instrument, those systematic errors, they are going to propagate in all the observations. So obviously there should be some error, some correlation error between the parameters, but that would be a higher order analysis. Like firstly we'll do the analysis with the completely independent case, then we can go and jump into the, we'll see how even the form of chi-square will change. We'll write it down. We'll do it tomorrow. I'm noting down, in case you have any suggestions for me, we can cover that topic. I'll try to include all of those in the tomorrow's sessions as well.
Yeah.
We are flexible that way.
Any more questions or? So we'll pause for a tea break. Let's keep it short because it's 11:50. So we give them 20 minutes?
10,
10? 15?
15 minutes.
10.
Okay, 10.
Okay, 15. That's in between. So 12:05, right? The sooner you come back, the better it is. And like Akshay mentioned, since it's a smaller group, right? The idea is that if people have individual issues, questions or whatever, please tell us, because we still have 2 more days. We can try to incorporate it in part of our talks or whatever, right? So if there's specific things you want focus on or something like that, do let us know. We will try our best to include it, right? So see you now in 15 minutes.